So now I'd like to show you an experiment which demonstrates very clearly that the classical electromagnetic theory of light as an electromagnetic wave breaks down at the atomic scale. Okay? And a very important experiment in physics called the photoelectric effect. We start with a vacuum tube. It's a totally evacuated glass tube of some sort. And on the two ends we have two plates of metal, okay? And we shine light on this one, and that is able to kick electrons out of the atoms, and they go off and they hit the other metal plate over here. Now, what makes them go there? Well, there's some electric field. If this is at negative voltage, clearly it's going to shoot the electrons to the other side, right? Because the force on the electron will be in the direction shown by the arrow there. And you'll be able to read the current on an ammeter here. However, in the 19th century, late 19th century, they started doing this experiment and they noticed a few peculiar things about it that it was really, really hard to explain. Firstly, the light that they shone on it, they tried to make monochromatic using a diffraction grating, which had been sort of recently invented. And so by turning the diffraction grating, you get light of different frequencies hitting this chunk of metal. And they noticed that there was no current in this thing unless the frequency of the light was above some magic threshold value. Okay? Well, that was kind of odd because in classical electromagnetic theory, you just have a wave hitting this surface and it should knock out electrons, right? It should knock out the charged particles and make a current appear across these two electrodes. Well, also, they saw that the current persisted even when the voltage was slightly positive. Well, when this voltage is slightly positive, does it attract or repel the electrons that are coming off? Attract it. That's right. If this is positive, the electrons, which are negatively charged, are drawn to that plate. However, if they kept increasing the voltage, at a certain point, the current would die. Of course, we have to be at a frequency above this cutoff frequency to have a current, but then it would die above a certain value of the voltage. Well, they kind of realized that must correspond to the energy of the electrons coming out here, which also violated what they thought from classical electromagnetic theory, which said there should be a broad range of energies of the electrons coming out. So how to explain that? You really can't explain it with Maxwellian electromagnetism. If the light is causing the electrons to come out of the metal, it shouldn't have any critical frequency, number one. And why should different metals have different stopping voltages and cutoff frequencies for the effect? Very, very strange stuff going on here. And perhaps the most strange is that the stopping potential depended on the frequency of the light. Nearly impossible to explain. Well, that wasn't the only thing back in the early 1900s which was difficult to explain with classical theory. And sort of the second nail in the coffin of light being a classical electromagnetic wave was what's called blackbody radiation. Now, it's kind of a misnomer because blackbody radiation refers to a glowing red-hot or white-hot object like an oven. So you can imagine you have some heavy cast iron oven, you heat it up some way to the point where it's actually glowing. Inside this cavity, you ask, what is the nature of the radiation inside? Because it's being emitted by the walls and absorbed by the walls and flying around inside there, and if you poke a little hole in the oven and look at the light escaping, and you could measure the spectrum of that light using, again, a diffraction grating and look at how intense the light is as a function of its wavelength, what you measure is this black curve here. At zero wavelength, the shortest wavelength, there's almost zero photons, and it rises to some peak and then falls off at very long wavelengths. If you heat the oven up higher, you find that this curve is displaced a little bit. The peak goes down, but still goes to 0 at 0 wavelength. If you tried to do this with classical electromagnetism and classical physics ideas, the prediction is that it should go up to infinity as the wavelength goes to 0. That is, as the light gets more and more into the ultraviolet, you should expect, by classical theory, to see more and more of it. In fact, this is a catastrophe, theoretically speaking, because it doesn't match the data that we had at all, and you get an infinity in your calculation. That's always a bad thing in physics. If you divide by 0 or whatever and get infinity, you must be doing something wrong. So they realized that there was a problem with classical electromagnetism. But how to explain this? Well, Max Planck, a German physicist, came along in 1900 and proposed an idea that he himself didn't really believe was true, but effectively it seemed to explain what was going on. He said that, well, maybe light comes as a corpuscle, which he called the photon, carrying a certain amount of energy corresponding to the wavelength of this little energy packet. And he did his calculations, and came up with a number, h. We call it h now, and it has the unit 6.626 times 10 to the minus 34th joules seconds. It's a constant of nature if Planck was right. Now, his notion was that light would be emitted and absorbed just one of these packets, one of these photons at a time. And so you can think of a photon as being a little wave packet. And here's what, if we could slow it down and look at it, what a photon might look like. It's big in the middle and tapers off on the edges. And it has sort of a characteristic wavelength and sort of a position around here somewhere. It's not well defined exactly where its position is. It's also, if we stop this and you were to try to measure it, it's not exactly clear what the wavelength is. If you were to take the difference, let's say, between this peak and this peak and this peak in space, you wouldn't get exactly the same number for crest to crest to crest. It does not have one fixed, definite wavelength. But it's pretty close to that, right? You can sort of measure what that is. It has a sort of average wavelength, which you plug into there to get the energy of this photon. So the energy of a single photon can be anything in Planck's theory, because the frequency can be anything, the wavelength can be anything, so h times that can be anything. And photons presumably move at the speed of light. And there's no reason not to think of them as being electromagnetic waves. In other words, the thing that I drew on the previous slide was what was indicating the value of the electric field, let's say, at that point in space and in time. So they really are electromagnetic waves. It's just that they're localized in space and have some sort of approximate wavelength. And they carry a certain amount of energy. It turns out to be really easy to calculate this energy. If we take the energy is equal to h times, well, in physics we oftentimes use either f or nu for the frequency. That's the Greek letter nu, not v. So it's hc over lambda. C over lambda being, f. The frequency. You take these two constants of nature, Planck's constant times the speed of light, and you get 1,240 electron volt nanometers. Something that this is one of those equations and numbers you should sort of memorize, because it makes it really easy to calculate the energy of photons, right? So for example, what is the energy of a green laser photon here with 532 nanometers? Let's do the clicker question. You probably shouldn't necessarily require your computer to do this. You just have 1240 eV, or your calculator to do this, 1240 eV nanometers divided by 532 nanometers. See, we conveniently put this combined constant into electron volts and nanometers.